To 6875, Cryptography and Cryptanalysis. We have two lecturers here. Myself, and Shafi will be co-lecturing this semester. We have three amazing TAs who are passing out your schedule: Alex, Josh, and Salih. The most important things to know in any class are pointers, right? If you have the right pointers, you can find all the information. And these are the 2 pointers. If you want to reach the TAs, this is the mailing list. The course website is stellar. If you know both these things, you can somehow find your way on. The office hours, TAs have office hours, and these are all posted on Stellar. What else is there? There isn't very much. The course prereqs that you will see in the course handout is just 6046. But really what we want is mathematical maturity. So, there are other security-related classes, actually even this semester at MIT, 6857, confusingly termed 6857, is an applied crypto class. It's sort of a less mathematical version of 6875, our class. There's 6858, I think, which is a security class. But really, 6875 is a mathematical class. So if you have, the reason we ask for 6046 is for mathematical maturity, that you can think about algorithms, think about analysis of algorithms, a little bit of complexity. So if you haven't taken 6046, no problem, come and talk to us. But the important thing is you should be able to do proofs, math proofs. Really, you should take a look at the problem set, at least the first problem set. It will come out this Friday. And if you can do it, it'll go swimmingly well for you. Okay, so that brings us to problem sets. There are 6 problem sets. The grade is almost entirely problem sets. There are 6 of them. There's an optional, 5 of them are mandatory, and the last one is optional. You can replace it with a course project, and we'll announce the details as we go along in the class. 6 problem sets. The problem sets will be out on Friday, so in particular the first one will be out this Friday, and it will be due 2 weeks later, so 2 weeks after same Friday. What else is there? Well, all sorts of details. There are late days. There are 6 late days, 1 per problem set, but you can take more than 1 late day on any given problem set. Let's say 3 on 1, but no more than 3, because we want to post solutions. What's there? Yeah. So if there's one advice I have to say up front about problem sets is start early. It'll be a mistake if you start the same day of the problem set. That's what my TAs tell me. They took the class last year, so first-hand experience. There isn't very much. So references, there aren't really formal references, but there are 2 textbooks that you can use for at least the initial part of the material in the class. We'll post all of these on Stellar. So just go to the Stellar website and you'll find all this information. Okay? And that's that. So let's do science. Okay.
Hi, so I'm Shafi Goldwasser, and I'm going to be assisting the lecturer-in-chief, which means that I will do most of the lectures, but I will be present here in some role. Okay, so this is 6875, and just a few more words, general words, before we get into the first topic. So, cryptography, a lot of you know about cryptography from the popular press and the fact that you use browsers and things come up, they say that things are authenticated or encrypted or end-to-end encryption and so forth, sort of real world. But this class, the emphasis really is on cryptography as it's based on mathematics and theoretical computer science, and also here and there we will talk about how cryptography has paid off dividends to theoretical computer science and even to mathematics because of various reasons. So just a little bit of historical introduction. When people talk about cryptography, so from an historical perspective, in the last 100 years, there are 2 people who come to mind. One of them is Shannon, Claude Shannon, who was a professor actually at MIT, and he in the 40s he published this paper called The Mathematical Theory of Communication, which is a very well-known paper where he introduces information theory. But apparently at the same time, he wrote another paper, which was classified, and only published, I think, about 10 years later, called The Communication Theory of Secrecy Systems, whose topic is all about cryptography. And he defines what security should be and so forth. And this is really going to be the topic of this first lecture. Then there was another person that you all know about, Turing, who invented the universal computing machine, but the public really knows him because of the movie. What's it called? There's so many movies about him, but the last one, The Imagination Game. The Imitation Game, okay. So he's very famous in the public because he broke the German Enigma machine, the cryptographic method that Germans were using during World War II. And it's kind of interesting that both of these figures, they were interested in cryptography. Shannon more in defining security, at least that's how we think of Shannon, Turing in breaking the Enigma machine. But they were also pioneers, very important figures in the history of computer science. Here, computer science, engineering, here the inventor of information theory, here the inventor of the universal Turing machine. So there's something about both cryptography and cryptanalysis that's very, very basic and interest in the history, and also I think in the whole fiber of computer science, and especially the mathematics of computer science. But the reason I put this slide up is to say the following, and that is that Shannon and Turing, they actually met each other, not that we care about their personal life, but also that movie does, but they met each other during the war, or so it says, that, and both of them were interested in cryptography because of wartime. I think that was true for Shannon, and definitely is true for Turing. That their interest in cryptography really gelled over this, the effort of World War II. And this is one place where modern cryptography, the subject of this course and all the courses that you see at MIT, differs. So whereas classical cryptography up to this mid of last century, it was really a wartime effort where you were really thinking about military applications, modern cryptography really comes into play with the rise of the internet, with the rise of the understanding that people are going to be able to communicate and with each other, and in fact, it's the enabler of secure electronic commerce. So you all have heard about RSA, I'm sure, being at MIT, and in general being a computer scientist. And really, this whole public cryptography and signatures, and a lot of what we're going to talk about in the beginning of this class, comes about because there's this realization that we're going to be able to do, communicate and do transactions over an insecure channel. So rather than talking about war, we're talking about commerce. And today, so this is not really the future, but then there was another evolution, which realizes that it's not just that we want to communicate over the internet and do electronic transactions, but we have a lot of data out there, and we would like to do computations on this data. But we also want, at the same time, to preserve some privacy of this data, because this data is often personal. So a lot of what cryptography is concerned with today, and also some things that we'll do in the second half of the course, rather than having to do with communication, they have to do with computation. So what I mean, so when communication, we want to send messages privately, we want to make sure that you know that it came from me, nobody modified it. But when we talk about computation, it's a different story. So we might have data that we want to keep private, we might have even programs that we want to keep private, and still we want to let other people execute them. And then we have to worry about both the correctness of these programs, say, and the privacy of both the programs and the data. So this is sounds very vague, but it is a big transformation from what cryptography was about to what it is about today. And the second half of this course we'll talk about that. And as I said before, that cryptography has also been, especially with modern cryptography, even beyond Turing and Shannon, it really brought up a whole bunch of notions to computer science and techniques that led to a series of leaps, really, in complexity theory and theoretical computer science. Pseudo-randomness, which will be a topic in the class, is something that was really originated by research in cryptography, and we'll talk about it quite a bit. There's the notion of interactive and probabilistic proof verification, which we will talk about from a cryptographic perspective. But while we are motivated by cryptography, and that's the topic for this class, you will learn some things that are basic, building blocks of theoretical computer science these days. Proofs, interactive proofs, probabilistic proof verification. And finally, I would say that the third sort of notion that you will get a side benefit of by learning cryptography is this whole question of average versus worst case hardness. And again, I think even in this class, we will say another word on that. So, this class has a theoretical focus, as you could already surmise from my from the first 2 minutes, okay, and also from what Vinod said. And how does that play out? Well, first of all, it's not that we're just going to tell you informally what encryption is about, but we will sort of actually define exactly what encryption schemes, what they're made out of, and what security definition we require from them, and what security definition we can prove for them. So definitions are going to be a very important part of this class. You have to understand sort of what security is in a formal sense. And we will also critique existing systems, so systems that people are using today, or are being proposed in light of these definitions. So whether they do obey the definitions or they don't, and how they fail. And often that's going to be done in the homework sets rather than in class. So I think the class is going to be more about the definitions and constructing systems that do satisfy it. But in your homeworks, often we will describe systems that are out there and say how do they fare with respect to what we believe is the right definition. Are we all good? You could ask me questions. I mean, there's nothing to ask here, but you could ask still. And then we will design systems where we can sort of prove that they are secure with respect to the definitions that we require. Now, those of you who know a little bit about crypto should be a little bit worried here. What do you mean prove? We prove very, when I say prove, often what the proofs look like here are we assume, let's say, that factoring integers is a hard problem. Or we assume, I don't know, that finding a short vector in a lattice is a hard problem. We will define exactly what a lattice is and what finding a short vector means, and so forth. But there are these assumptions that we make, and then when we talk about proofs, we really mean proofs of this sort, where we design a crypto system, okay, and then we prove that it's secure. What does it mean that we prove that it's secure? We actually present what we call a reduction. Okay, what is the reduction from? We say, if there was someone, okay, an adversary or an enemy that had a strategy that could break our crypto system, and break has to have some formal sense, right? We have security, and then breaking the security is violating it, right? So if there was an adversary strategy, someone had an algorithm, that he could break our crypto system, and he could do it in some time, let's say T of K. What's K here? K is, you will see it later, but all throughout the course, we always have something called a security parameter, which is K. I mean, maybe it would be N, I don't know, but it's a letter. And what do we mean by that? It's a size. So we could say the security parameter is 100, or it's 1,000, or it's 2,000, you know, usually it's powers of 2. But, so in any case, and then we will talk about things being efficient in polynomial in K, or exponential in K. And K can change as technology changes. But in order to set everything, kind of anchor everything, we usually have a security parameter, and we talk about time as a function of K. It could be a polynomial K, like K, linear K, running time, 2K, K squared, or it could be exponential, like 2 to the K. Are we good? And efficient and inefficient will be with respect to running in polynomial time or exponential time, the rough divide. So in any case, back to this, how do we prove security usually in this class? We say if there was an adversary that could break the system, and he could do it in a certain amount of time, function of the security parameter, and he could do it with some probability. Again, this is just so you get some mental picture of how things look like here. You don't have to remember this. Then we show a reduction, how we can use that adversary, sort of as a subroutine, because he exists, we assume it exists, in order to solve some problem, some hard problem in mathematics, in time that's related to this breaking time. So the breaking time was T of K, now it's going to be some a polynomial in T of K. So the breaking time was K squared, it might, solving the hard problem might be K to the fourth, okay, but it's still polynomially related, and also with a probability which is related. So this was, let's say, probability 1/3, this might be probability, 1 in 100, I don't know. 1/3 divided by all. So this is, again, just to have a template. The proofs here usually are going to look like reductions. So you understand the logic? The logic is this. Why is this a proof of security? Because we're saying, well, if this really is a hard problem, then it's impossible to solve it in this time. And therefore, it couldn't have been that the original adversary existed. So it's sort of the proof of security, because it says, listen, if it's not secure, so there exists someone who can break it, we could use it to do something that's impossible. That's how these proofs would look like. But if you think of, so that's the conceptual framework of the proof, what is involved usually is actually an algorithm. You have to develop an algorithm, okay, to solve hard problems using some magic adversarial strategy which might exist. Okay? I know that usually you're taking classes in algorithms. It's not like this. You actually design an algorithm because you want to run something fast. In this class, often you're going to be actually designing algorithms just as a way to prove security. Because you're going to say, well, if there was an adversary strategy, then I would have a really fast algorithm. Okay, so in some sense, what this means is that either way science wins. Why does that? What do I mean by that? It means that we're going to design crypto systems that either they're fantastically secure, or if somebody managed to break it, because they put a lot of work into it and they really want to break it because they hate us or are the enemy or whatever, good, then they will solve hard problems in mathematics we didn't know how to solve before. It's weird, but that's what goes on. And in fact, if you think, anybody here heard about quantum computing? You must have heard about it. And some of the big impetus that quantum computing got, in fact, probably the push, was an algorithm for factoring integers, which was invented by Peter Shor, who was a professor in the math department, on a quantum computer. And now we don't have quantum computers yet, maybe we will, not yet. But he worked on trying to factor integers on a quantum computer because factoring is a very important problem for cryptography. So in some sense, he did play out in the quantum arena. He was sort of saying, well, if I can factor, I can break some system. And then he actually put a lot of effort and could factor on the quantum computer. Anyway, it's a side story. So again, our proofs are always going to look like reductions. We're going to design a system, and then we're going to say this system is secure if some hard problem is really hard. And the way we prove it is we say, well, if you could break it, that hard problem becomes easy. Good. So that's all I think I wanted to say about sort of generalities. Of course, it's all conjectural, which hard problems. I mentioned factoring. You probably learned about NP completeness. So you would ask, well, why not some NP hard problem? How many people here know about NP completeness? How many people didn't take 6046? Because they do teach that in 6046. So it's not an integral part of this class, but these are concepts that you need to be familiar with. You know, what are hard problems? What's NP hardness? So hard problems, in fact, come from lots of places. Number theory, geometry, coding theory, learning theory, combinatorics. And as we go along, we will show examples of problems which we believe are hard and are useful for cryptography. Okay, they're not going to be incomplete problems. There will be something else. And we will, when the time comes, we will define the problem, we will show why it's a good problem for cryptography, and we'll tell you the best algorithms that are known. So this is the evidence that we have these problems are hard. Okay, I'm going to jump. In a minute we're getting into the real topic, but here's the topic of, this is essentially a list of topics of the class. You also have a schedule out, right, which goes lecture by lecture. What we'll be doing is we will do encryption, we will talk about digital signatures, we will talk about pseudo-random number generation, we will talk about zero-knowledge proofs, we will talk about two-party secure computation. This is already sort of shifting from here. We're kind of shifting from from communication to other things. Other things here might be verifying. Let's say you can think of this as zero-knowledge proofs are mathematical proofs that have this interesting, unusual property, and that is that at the end you'll be convinced that if the mathematical claim is true, but you've learned, in a sense, nothing. Or specifically you haven't learned how to prove it to someone else. So this is a very natural in the cryptographic setting, because what I might want to prove to you is that a mathematical fact that only I know the proof of. And at the end you will convince of the proof, so I must have known it, but you won't be able to prove it to someone else. Again, we have to get there, but it's related to identity theft, preventing identity theft, rather. And these days you hear a lot about zero-knowledge proofs also in the context of cryptocurrency. You may have heard about this. People talk about sort of smart contracts, and you might talk about zero knowledge in that context. Then we're going to talk about two-party computation and multi-party computation. That's sort of the later half of the class. What do we mean by that? Now we mean that we're not only communicating, but we're actually computing functions. So what could be a function? Say Vinod and I are players, and he knows how many lectures he's going to give, and I know how many lectures I'm going to give. But we don't exactly necessarily agree. And we compute the two-party algorithm at the end to know whether we agree or not, for example. It's not clear why we want to do this in privacy, but you could imagine a situation, which is not a joke situation, but you know, people talk often about the millionaire's problem. So he's a millionaire and I'm a millionaire. It's theoretical.
That's not fair.
And we get to know who's wealthy. And well, we don't want to tell each other how much we have. Okay, so we want to essentially know whether x is greater than y, right? How do we do this? How can we compute whether x is greater than y without giving each other x and y? So it turns out you can do that. In fact, you can do any two-party function in such a way that at the end we'll know the result. And the result might, of course, tell us what the inputs were. But not always. Like the x greater than y doesn't tell me what x and y is. Just that it's greater. We'll be able to do that with just revealing the output and nothing else. And furthermore, we can even do this not just with two people, but you know, the whole class can be computing something. I don't know, the average of something, or something more sophisticated than that, like a vote. You want to know whether the tally is. What the tally is without knowing who voted for what, and more generally, more interesting things. You could do that as well, where people would know what the outcome is, they would know what their input is, maybe what the inputs of their friends are, but not what the input of other people are. And again, this is based often on believing that some problem is hard, like a factoring integers or something about geometry, and sometimes even without those assumptions. You know, we have some other trust assumptions, like that this class, maybe you have 10 friends, but no more. So 10 people tell you your input, but not everybody else. Or maybe half of the people, but not less than half, and so forth. So these are the type of assumptions. And notice that I went through a whole slide and I didn't use the word machine learning. I should be commended for that. Okay, I could have. I didn't, in fact. And what I have here is de-randomization, physical zero knowledge, and Byzantine agreement, these kind of things that show up here. They're supposed to be in different color. What is that? These are side topics where cryptography has actually made a difference in other areas, like coming up with random numbers, sort of de-randomizing algorithms. The zero knowledge has had a curious application to physics, disarming nuclear warheads. So this, like using a zero knowledge protocol, some weird application that was born in Princeton, but there are people at MIT now in the nuclear engineering department who work on it, where let's say the Russians in the US, they agreed that they're going to disarm nuclear warheads, but they don't want to show each other the technology. So how do they know that when they're, disarming them, that they're actually using nuclear warheads and not some demi? So there's some sort of zero knowledge protocol, which is using physical means, obviously, not just mathematics, where you know that this thing is a nuclear warhead rather than something else. I know it sounds science fiction-y, but the truth is that people who are in nuclear engineering that has very large grants from the government to implement these zero knowledge protocols. So it has had an interesting principle to other fields, and Byzantine agreement is something from distributed computing where you've got a whole bunch of people that want to agree. Again, cryptography has been useful for achieving it. So this is really kind of just throwing it out to you so you know what you're going to expect to learn throughout the term. This is really cryptography that we could have been teaching 15 years ago, because there's so much more that would probably fill like at least two other courses, but we're not going to get to it. So there's always a trade-off here where we're going to give you everything, or we're going to try to go in depth, and the lecturer-in-chief has decided that we will. This is the outline. Okay, what?
We'll see how it goes.
We will see how it goes. So now let's start talking about this unit. So one thing throughout the course, and beginning with this lecture, is what unifies all the topics that I put on the previous slide, okay, is that there's an adversary. Whether we're talking about encryption, digital signatures, the like computing functions, he's the adversary or I'm the adversary. So zero knowledge proofs, the proof you always think about the proof as sort of a process of convincing a suspicious, a proof in some sense, I'm proving a theorem, it means that you don't trust me, right? So in a sense, I'm an adversary. So in any case, there is an adversary always in all the lectures. And that sort of defines it's an integral part of defining the problem, and also who that adversary is and how strong they are will determine what is an acceptable solution. If it's a very weak adversary, solutions can be easy. Right? If it's an adversary, doesn't have much computational power. It's a very strong adversary, the solutions have to be much more robust, even to work in presence of this strong adversary. So you always have to think, who's the adversary? You'll see this also in your homework problems. The adversary has different powers. In the first problem, at least, from what I remember. Okay, so let's start. So the first problem that we're talking about in this class is really secure communication. So we're still in communication, and we always have these two parties, which we call Alice and Bob. I think they were introduced in the first RSA paper in 1977. And Ron always likes to joke that regardless of what stays from that first paper, Alice and Bob have remained forever in the history of computer science, which is true. They use it all over the place. And what Alice and Bob want to do is she wants to send him a message, but there's someone who's listening on the line. So there's an adversary who wants to know what the message is, so she's not going to just plainly send it, okay? Rather, what she's going to do is that she is going to meet with Bob to agree on some secret key. So this is classical cryptography. Alice and Bob, before the beginning of time, okay, they agree on, they meet, and they agree on something that we call a secret key. And S for secret key. And now they know it, okay? And now, and what is the length of the secret key? That's going to be what we're going to count how many bits are it. We're going to think of the secret key as a string, right, of bits, and we care about what the length of that string is, and that's going to be what, for this lecture, will be the security parameter that I talked about, right? So let's say that the log base 2 of S, or which we usually denote also like the length of S, is not a cardinality, it's like the length of the string, how many bits the string is, will be the security parameter. I think that in the rest of my slides, it's K. So they agree on the secret key, and then based on that, instead of sending a message, they send what we call a ciphertext. So part of this lecture is introduced to kind of terms, right? So M, to begin with, was a plain text. And now she's going to be sending across C, which is a ciphertext, which we're going to call ciphertext. And this ciphertext, right now, there's a placeholder. In a minute, we'll say what this E is. This ciphertext, what is it? It's the result of computing some algorithm. This is an algorithm. Later we'll call it an encryption algorithm, so it's E, okay? And applied to what? To the secret key that both Alice and Bob know, and to the plaintext, to the message. And so she sends a C rather than M. So what would you naturally hope? Obviously, you would hope the fact is that first of all, Alice can do this computation. Second of all, Bob is able, because he knows what S is, to recover what M is from C, right? Because he needs to know what the message is. And the adversary shouldn't be able to. Why shouldn't the adversary be able to? Because it doesn't know what S is. It's sort of clear what you want. So let's define this a little bit more, okay? So from here on, this is the definition of what an encryption scheme should be. So an encryption scheme is actually a triplet of algorithms. It's not a single algorithm. Okay, why a triplet? And these algorithms, by the way, they can be deterministic or they can be probabilistic. So you've all seen what a probabilistic algorithm is, right? Because in 6046, there's some lectures on that. Who hasn't? Well, you're not going to admit it. Who has? Okay, well, I guess just by pigeonhole or whatever it is, by counting argument, there's something about it. So there's a triplet of algorithms who could be both, possibly deterministic, meaning that on the same input they all give the same output, or probabilistic, which is on the same input they also toss coins, and then you have many possible outputs. That would be enough for the sake of this lecture to define probabilistic algorithms. So these are probabilistic algorithms, and what is the meaning of them? So there's G, there's E, and there's D. G really is an algorithm that takes a security parameter as an input. And here already you see that it's probably annoying, but it's the first annoying place that you'll get used to it. We want this this algorithm G to run in polynomial time in the security parameter. Polynomial time, again, it looks like K to the C. So just to be formal about it, we need to say that the input to this algorithm, because always we talk about algorithms which are polynomial in the length of their input, right? That's basic from 6046. Polynomial in the length of your input. So the input has to be at least length K, but if I just gave it K, the input would be what length? Log K. That's why we have this, terminology of sort of K unary, so like 1K. K is the input size, and this guy can run polynomial in K. Now, what is the purpose of this G? First of all, I'm going to call it a key generation algorithm. The purpose of this G is to output the secret key. So in the previous slide, the secret key was S, right? So G is this process where they meet and they agree on the secret key. I didn't specify how they choose the secret key, right? I just said that there is some procedure. But if you want to nail down the encryption algorithm, you have to say what Alice and Bob have to do. So that's the key generation algorithm. So this thing outputs, let's say, some secret key and of length k. That's okay, what we call S in the Alice and Bob picture. What does the encryption algorithm do? It takes the secret key and the message and outputs a ciphertext, little c. And what does D do? D is a decryption algorithm. So if you can encrypt to produce C, the decryption algorithm is what Bob will run on the other side. He also knows the secret key, and he only got the ciphertext, and somehow this should be enough for him to output some plain text, M prime. Now why do I say M prime? Really well, because when you specify an encryption scheme, we just specified sort of G, E, and D and what their input-output relations are. That is, this guy takes a ciphertext and outputs a plain text. Okay? And now what is it that you want for this whole thing to make sense? You want two conditions, and that is you want what we call correctness and you want security. Okay, so what would be correctness here? Correctness naturally would be that if Alice encrypted M, Bob will decrypt the ciphertext to the same M and not to some other message. So correctness is that that this M, in a sense, if ciphertext here is the encryption of M, then when you decrypt that, you get an M prime which is equal to M. Okay? So, in other words, that's just what you would think it should be. So correctness here would be the decryption of the secret key of B, and the result of applying encryption to M should be M. Correct? For all messages. Now, any questions? So that's kind of obvious, right? There's one other thing that's going to make an appearance in this lecture. Sometimes we omit it in future lectures, and that is that we have some notation for the space where these messages come from. So we have capital M to talk about the message space. So if you'd like to think of an example, message space English. Like it's English words are a message space, or it could be just 01, or it could be something else. Okay, but there is some sort of a message space. Okay, and these M's they come from the message space, and in fact it's not just a set; it's a probability distribution. So some messages are more likely than others. If you think about the English alphabet, Z's are less likely than E, right, and so forth. So when you think about a message, I'll write M, but we really think about a probability distribution. Namely that, M, if we think about various messages, MI might have a probability piece of I of showing up. So you really think about this as some probability associated with throwing a message in this message space, okay? I'm not going to use this notation. So correctness is one thing, and then I. So I mentioned the message space, okay, with M over here, we call it the message space. And again, I said it's actually a probability distribution over the message space. There's also, in this lecture, capital K will denote the key space, where these secret keys are coming from, and capital C will denote the ciphertext space. Okay, so where these ciphertexts are coming from. So this is something you'll see in this lecture. We will see capital K, which is the space of secret keys, and capital C, which is the space of ciphertext. All right? And also, capital K will have a probability distribution, which is how, keys are distributed. And similarly to ciphertext, which is sort of induced by the probability distribution over the messages and the key space. Right? So you choose a message with certain probability, you choose a key with certain probability, right? And now you apply the encryption to the secret key and the message. Again, details that are not so important, but these are the players that are going to show up on the slides here. The generating algorithm, the encryption algorithm, the decryption algorithm, and then these words, plain text, ciphertext, and these spaces where the plain text comes from, which is the message space, where the ciphertext comes from, which is this big C, and where the keys come from, which is big K. All right, what else I want to say? There's a lot of, you could talk about this definition for a long time, okay? Even here, before we define security. So for example, I said already out front that these algorithms could be probabilistic algorithms. okay? Which means that on the same input there's many possible outputs. So for example, the algorithm that generates keys, okay? What if it was deterministic? That would not be a very interesting scheme, because it means that algebra always had one key, you know? And you know, and the adversary would know what it is if you knew how their procedure. So the generating algorithm is always randomized. There are many possible keys that can be picked up. And in fact, in some sense, one strategy for breaking a scheme for the adversary, right, is just to try to find out all possible keys and try one at a time. Say, I think that, you know, if you could enumerate all of them. So naturally, there should be lots of keys, because this trying all possibilities, this exhaustive search should be expensive. Should be more than polynomial in K. Now, what about the encryption algorithm? The encryption algorithm, what does it do? It takes a message, and it's a fixed message, a fixed secret key, and outputs a ciphertext. It could be deterministic, which means it's always the same ciphertext, but it also could be randomized. It could be that on the same message, you get lots of possible ciphertexts. And we will show fairly early in the course that unless it is probabilistic, unless there are many ciphertexts for the same message, there's certain security properties you can't get. So if it was deterministic, there's some things you just can't be too secure in some sense. The last thing is, what about the decryption algorithm? Here you would say, here are no problems, right? Same ciphertext and secret key, you should get the message, because my correctness requirement was that that you should get back the message you encrypted. So should the decryption algorithm be randomized? Should we allow it the liberty of being randomized? Well, first of all, sometimes we don't know how to do things deterministic without tossing coins. So tossing coins is useful for me, because I don't know how to solve the problem differently. Even if the solution is unique, I might need some randomness to help me. So do you guys remember primality testing? Did you do that in 6046? So remember, there are some primality tests that need randomness in order to get the right answer, but they need randomness to perform. Okay? But furthermore, and again, maybe that will be some homework assignment, sometimes we say, you know what, that's too strict a requirement. I mean, it makes sense. We want to make sure that if I send you M, you get M and not something else. But if, you know, 1 in 2 to the 100 probability you'll get something else, I say, you know what, so be it. You know, anyway, with probability 1 in 2 to the 100, I don't care, you know, because something else will happen. Like the world will end or something like that. So sometimes you say, with high probability. That's something you'll see a lot. Okay, you say, we want it to be M with high probability 1 minus negligibly small. Now, why do that? Maybe that's all we can achieve. And therefore we say, you know, that's good enough. Or maybe by allowing the definition to have with high probability, we can get some extra. What is something extra we might get? So just sort of to throw out to you sort of the juice flowing is, for example, we have this notion, which again probably we might get to it, I think, or in homework, we call deniability. What is deniability? So you've all followed the election, you know, Hillary Clinton, emails, you know, whatever. Wouldn't it be nice if I could send a message, but later claim I sent something else? And even be able to prove it. That's a deniable encryption scheme, where I can prove that I sent 0, or I can prove that I sent 1. Now, obviously you want to make sure that the person that I sent it to knows when I sent 0 or 1, or maybe I can prove to some third party, either way. And you couldn't do that if it was absolutely the case that it always gave back the message that you encrypted. But if you had this high probability, and there was some little chance, 1 in 2 to 100, that I sent something else, you could use that as an in to have an encryption scheme that has this extra deniability property. Weird, but true. Okay? So all of these definitions, once you relax them a little bit by allowing a little probability of error or allowing randomness, all of a sudden new things become fluent, and we will see that in the homework assignment. That by tweaking the definitions slightly, we can do things we couldn't do otherwise. And yet, the definitions are good enough in the sense where if the person on the other side, the probability 1 minus 1 in 2 to 100 gets my message, but meanwhile I can deny to everybody else what I sent, I'm willing to deliver it. Okay, so let's talk about, I'm going to skip this. This is it'll be in the slide, something about Caesar code, Enigma, machine, get that. Let's talk about the first real formal definition of security, and that's in Shannon's work, which I referred to a few slides ago in this paper, Perfect Secrecy Systems, and I hope that that will be on the website. We should post that paper. It's a really fundamental paper. And as I said, first of all, we need to decide who is the adversary. So the adversary in this lecture is all-powerful. What does that mean? It means he has no computational limitations. He can run in exponential time. He can use exponential space, okay? And we have to have a system which is secure even in front of such an adversary, which doesn't exist, but it doesn't matter. If we can prove that it's secure for him or her, then obviously it's secure for anybody. Okay, so suppose the adversary was all-powerful computation, okay? Could we, this is what we're going to do today, could we have a system which is secure? And we will see that miraculously, yes. So we'll define security, we will show a system that's secure for such an adversary, but the end of the lecture will be a little disappointing because even though it's secure, we can't really use it in the internet, you know. It's one of those classical systems where Alice and Bob have to meet in advance and agree on a key. And me and Amazon, we're not going to meet in advance, okay? So this is not really, but it's incredible to see that you could get the best security imaginable even in the presence of an unbounded adversary. But in order to get the kind of systems we use today, the adversary that we consider is weaker. So this lecture, let's be kind of clean and pure and do it, okay? So what does the adversary know? So we said that he has unbounded power, but he's not clairvoyant, okay? You know, he doesn't know what I think. Today at least. Maybe he does. But anyway, so who is the adversary? The adversary is unbounded computationally, but what does he know? He can see the ciphertext. That's one thing he can see. So we're in the Alice and Bob picture, right? So Alice and Bob meet. Where is it? Here. This is the adversary. No, he doesn't see the message anymore. He sees the ciphertext. These guys know the secret. I don't know, we can call it a secret key now. The adversary, he doesn't know the secret key, but he does know ciphertext. And he sees the ciphertext going along the line, and now he applies his unbounded computational power. Okay? What else does he know? We are going to assume that the adversary knows what these algorithms are. So he knows G, he knows E, and he knows D. So in other words, he knows what procedure Alice and Bob went through in order to come up with the secret key. That doesn't mean that he knows the secret key. Because recall that I said that the generating algorithm here, that generates the secret key, is a randomized algorithm. So when you run a randomized algorithm, so this is a randomized algorithm. So it takes the input, which is 1 to the k, by the security parameter, and it outputs a secret key. But in the process here, it tosses coins. Like it has a coin, and these coin tosses, they will be different executions, right? And depending on these coin tosses, there are going to be different secret keys. So the adversary, this is called Kirchhoff's law, he knows which system is used. He knows sort of what G was run, and what E was run, and what D would be run, but he doesn't know what doesn't he know? Well, he doesn't know the internal coin tosses in the case of G, he doesn't know the secret key in the case of E, and he doesn't know the secret keys in the case of D. Okay? So there's something he doesn't know, but he does know what the procedures were. Now, why assume that? Why not assume that the adversary has any idea of what algorithms I'm using? Did I use RSA, or I use some other magical thing? Why do we let the adversary, why do we assume that the adversary knows this? And this is, again, sort of a mathematical point. The point is not that we go and we tell the adversary, you know, I use RSA, you know, or here's my code for G, E, and D. That's not the point. The point is because this is a theory class, okay? And because I can't assume that he doesn't know it. It's very unlikely that the adversary isn't going to know what system is being utilized. You know, whether particular people use RSA or use some other system. So we're saying, you know what, let's assume he does, and we want to prove security, even though he does know. So if the more I let the adversary know, okay, and yet I can prove security, the better situation we're at, right? And it's reasonable to assume simply that the adversary knows what G, E, and D is, and still we can fool him. People understand that? This is a question that always comes up here. No question. I explained it so clearly. Okay, so what's security? So now we need to define security, right? And define correctness, now we should define security. That's the thing that's missing. So what should be impossible for the adversary? Anybody can tell me? So an adversary that just saw the ciphertext, but doesn't know what the secret keys are, and he doesn't know what the G, E, and D, what the code for G and D is, except he doesn't know the internal coin tosses. What do we want to? What could we want from security for the system? Well, we certainly shouldn't be able to learn what the plaintext is. Everybody agree with that? because then the string really is not very good, is it? Might as well just send the thing. So that's definitely the case. So he should not be able to, it should be impossible to compute the plain text from the ciphertext. But is that good enough? Well, we could ask for more. We could say he shouldn't be able to tell what the first bit was, or what the ith bit was, or maybe what the exclusive OR of the bits is. Or more generally, any partial information about the plain text. That would be better, right? Good. And we want him to not even be able to successful with small probability. Correct? And we want this to be true for maybe all messages, not just some messages. It shouldn't be true that some messages he can recover and some messages he shouldn't recover, right? In the best of worlds, he shouldn't find out any information about the plain text for any message, right? Regardless of what ciphertext he sees. And another thing we could say is that he shouldn't be able to compute relationships between things. Say Alice and Bob send more than one message at a time. You know, I send message 1, then I send message 2, message 3. I don't want him to know whether I've sent the same message twice, whether they have the same prefix or not. You know, I think the enigma story is that the Germans used to say, send messages, but there was always a greeting in the beginning. The same greeting for every message, and that was something that, you know, the breakers took advantage of. Okay, so we want to do this. So how do we define that? So the first security definition, which is really the first thing you need to, first sort of deeper thing in this class, besides setting notation, is what we call a perfect secrecy. Perfect secrecy. And in this class, sometimes we like to call it Shannon secrecy, because that's the definition that Shannon introduced in that paper that we're going to post, okay? In that first paper on cryptography. Here is what perfect secrecy, or Shannon secrecy is. So recall that the adversary, we call her Eve here, is an unbounded, okay? The truth is, because she's unbounded, she's not really going to be explicitly mentioned in this definition, okay? But just think that the whole definition is with respect to Eve, is unbounded adversary. And what we say is that an encryption scheme, so this triplet of algorithms, G and E and B satisfies this definition, is perfectly secret if the following is true. That for every big M, so for every probability distribution over message space, whether it's English or I don't know, Hebrew or Hindi or Chinese or whatever, so for every probability distribution over the message, okay, for every ciphertext that goes on the line, okay, and by the way, I'm going to assume, so this is, I'm going to, so when I say for every ciphertext in C, I'm going to assume here the probability, well, we'll say it in a minute. So for every possible ciphertext that you see on the wire, every single one of them, okay? And for every message in the message space, so this could be even very low probability messages. So messages which have non-zero probability. So I'm sort of making an assumption here is that this message space doesn't have any zero probability messages, and same for the ciphertext. Every message and every ciphertext has some, because I want to be able to divide my probability of a message, and I don't want to be able to worry about dividing by zero, okay? So just have technical definition. So for every ciphertext and for every message, it's going to be the case that the probability, and now the notation here is this is a random variable. The probability that the message that will be chosen is little m, so this is a real value. I mean, this is a concrete value of a message. And when I write this notation, probability of big M is little m, is the probability that this is the message that was chosen. Okay? So it's a little bit of abuse here because I don't know how to draw italic on the board. So it looks like this M and this M are the same. So why don't we just say that they are the same, and I have abusing notation. Here I'm thinking about it as a probability distribution. Here I'm thinking about it as sort of a random variable. So for the probability that the message that's shown is little m, as far as the adversary is concerned, is the same as the probability that the message was chosen as little m, given that the ciphertext that you saw is little c. What does this mean? This is it. This is the definition. What this means is, look, the adversary, we said, he knows how you send messages. He knows G, E, and D. He also actually knows the message, whether you're going to send messages in English. So he knows, let's say, the probability distribution over your message. Okay, so he knows big M in probability distribution. there's still, now you are actually sending a particular messages. Either I'm going to send zebra or I'm going to say hello. Zebra is less likely, I think. It depends if you work in the Zoom. But in any case, so the probability that this particular message came up, he knows what those probabilities are. We want to say, so this is sort of the a priori probability. We want to say now the adversary, he's actually seeing the ciphertext. So the ciphertext that's being chosen, so again, this is sort of a random variable denoting which ciphertext was sent. He knows it's little c. So this is conditional probability notation. Now, does that change for him the probability that I send zebra? So this is the a priori probability before he saw the ciphertext, and this is the a posteriori probability after he saw it. You absolutely have to understand this definition. Any question? Yes?
Should the same also be true for probabilities over keys?
Yes, so good question. So what is these probabilities over, right? So here are the probabilities just over the choice of messages, right? The probability distribution of the message space. Here are the probabilities over M, but also over the choice of keys, right? So it's over the secret keys. You're absolutely right. So that's your question, right?
No, my question was really, or maybe I'm not understanding, but I was wondering whether this property should hold if you replace the random variable n with one representing a distribution over keys. So here if we have, so the a priori probability of any key should be equal to the conditional probability of that key given. So is that also?
So in this definition, there's no mention of keys, right? On this side, on the left-hand side of the equation. The left-hand side of the equation is just the a priori probability. There is no crypto. It's just a choice of what message I want to send. So here it doesn't make sense really to mention keys. Maybe it would be easier if I wrote this way. So this is a priori probability, and this is the probability that when I apply E to a secret key and to a message, you get back little c. Okay? So I'm saying the probability this is what was sent, little m, given that when you apply the encryption algorithm to the secret key and that little m, you got little c. Okay? And this is taken over this choice of the secret key. I did it in capital especially, because that denotes a random variable. So I have all, little letters, that's like a concrete value for the message, for the ciphertext, for the key. Big letters is sort of, the random variable that denotes which message was chosen, which ciphertext was sent, which secret key was selected. Is that clarifying? I'm not sure. Maybe you understand the question.
So I guess you could come up with a definition where M was replaced by K, but then the semantics of that is that you want to hide the key, right? But really you want to hide the message. We could come up with it. You could write down the definition, but it's not clear what that means. It's not clear why you want to hide the key beyond hiding the message.
Is that what your question was about?
I guess my question was whether for perfect secrecy you would have to append that definition as well.
No. So in fact, let me clear. What's your name? David. So you know that slide when I said what is it we want? That we want to be able to make sure that you don't get M from C? There should have been one line before that, which is from seeing C, you should be able to know the secret key. And then you're saying, well, maybe we want, so that would be obvious, because if you knew the secret key, everything breaks, right? But we're asking them less or more. We're asking more. Not only they couldn't know the secret key, you couldn't know actually as partial information about the message. So you don't need to append it. This will be implied, because in some sense, if this is true, obviously you cannot find a key, in fact, stronger than that. Yeah?
Actually, I think it's not true, because if you have some, distribution message, say messages in English language, and you see a ciphertext, you get information about the key that way. It's just that information you get happens to be completely useless for figuring out what the message is. I'm assuming we're talking about one-time time, but but you do get information about the key.
If your scheme is weak, if your scheme was weak, okay, you're not talking about definitions. You're just saying maybe you have a weak scheme where kind of the key is transparent from it because you knew the distribution of the message space.
Yeah, like in a one-time pad, if you know the message in English language, then you know ciphertext, and you know then you have a stronger distribution of the key now.
No. So
It's not uniformly argument.
I mean, also in a sense, you were saying that you will know some, it restricts your distribution over the keys.
Yeah,
Yes,
it's just useless to figure out the messages.
yes, yes, right. Okay, good point. He makes a good point, you made a good point. But we don't need to append the definition because what we want really is to hide information about messages, not necessarily hide information about keys. To the extent that knowing something about keys will tell me something about messages, we're going to hide it. Okay. So the key, let's think of an artificial example. The key is such, it's a long key, half of it I never use. Okay? If you find that out, I don't care. But I do care to find out the part of the key that will compromise my plaintext. Yeah.
Oh, if I send the same message twice, will the ciphertext be
Great
the
question.
same?
Great question. I haven't actually proposed an encryption scheme, have I? We are jumping the gun.
I think you,
So far,
you
just
mentioned
propose a
it
definition.
before.
He mentioned one-time pad.
Oh.
Or somebody mentioned, you mentioned. Whatever it is, nobody else has heard about it, okay, at this point. All we've done, so we will get to it in a few minutes. All we've said now is that there's a way to send actually a single message. All I told you is that there's a way to encrypt message, and there was a way to decrypt message. I didn't tell you to use it, I didn't propose a scheme. I didn't propose a scheme yet. There are schemes where what you said would be a problem. Okay, but let's get there in a minute, okay? So far we just said that there has to be 3 algorithms, there has to be correctness, and there has to be security. And this is a security definition. The security definition is extremely strong, okay? It says that whatever thing you know about the messages that are being sent in the English sentences does not change even though you actually saw the ciphertext. The a priori and a posteriori probability are the same. It's hard to imagine something stronger than this. So you might as well not look at the wire. Right? If the probabilities don't change. Okay, let me give you one other definition, and then we will show something about this definition. Okay? People understand the definition. Whether you see the ciphertext or you don't see the ciphertext, it makes no difference in terms of your probabilities of which message is sent. Okay. What's another possible definition? So the thing about definitions that you'll find out in this class is that I think sometimes, especially in mathematics, right, which has been around for so many years, is that when they tell you a definition, it's like, this is God saying. That is the truth. So we are not so religious here. So in a sense, we propose a definition, and maybe you don't like it. So, and maybe you're right, and maybe you're wrong. We can argue about it. So one of the ways that people have argued in cryptography and kind of convinced themselves that something is the right definition is they propose several definitions. All of them sound reasonable, say, and then they show they're equivalent. And by showing the definitions are equivalent, it gives you more confidence that you actually hit on the right definition with the right, idiosyncrasies. Okay? So here's another definition. And this is a definition which I'm going to call perfect indistinguishability. Okay? Perfect indistinguishability. Again, we've got this unbounded adversary. Perfect indistinguishability says the following. Again, we will say that our triplet of algorithms, our encryption scheme, satisfies perfect indistinguishability if the following is true. Again, if for every probability distribution over n, over the message space, okay, the following is true. Take any 2 messages in the message space. So this is we only need one universal quantifier, okay? So it's not for all, but it's for all m prime, for any 2 messages, okay? In the message space. And for any ciphertext in the ciphertext space, okay? It is the case that when you see this particular ciphertext, the probability that that's the ciphertext you see, given that the message that was chosen is little m, is exactly the same as the probability that you see this ciphertext, given that the message was chosen was m prime. In other words, another way, if I just spell out what this means is the probability that when you choose little m, okay, and you choose the key, you apply the encryption algorithm to the key, the secret key, and little m, you get little c, is the same regardless of when it's little m or little m prime. So what are these probabilities taken? These are taken over the choice of the key, secret key. What does this mean? It means really that having chosen the little m, okay, on this side of the equation, there's still the freedom to choose the little k, the k. Right? And depending on what k, on the secret key, and depending on what secret key you've chosen, you will have different ciphertexts. Right? So now that little m is fixed, right, there's still some degree of freedom, which is choosing the secret key. And we're saying, you know, you could just sort of enumerate all possible secret keys, all the probabilities that they have been chosen, and that will give you, induce probability to what ciphertext comes out, right? You with me? Right? Remember, E takes, the encryption algorithm takes as input a secret key and a little m. And then it produces a little c. The secret key was output by running the generating algorithm along with the k. Then lots of possible secret keys, right? And therefore lots of possible ciphertexts. And I'm saying the probability of a particular ciphertext going along, given that you started with little m, is the same as if you would start with little m. What does that say? It says that from the ciphertext going on the line, you can't really distinguish whether m was sent or m prime was sent for any pair of messages. So for any pair of messages, they're equally likely given the ciphertext. So this is a different flavor definition. The first definition said that really the probability of the messages are the same as far as you're concerned, even if you saw the ciphertext. The second one says from seeing for every pair of messages, you're focusing on two messages. Those you know that either it was sent yes or no, you know, attacked or not attacked, okay? You would like to know which is the case. We're saying from the ciphertext, no idea. You know that two messages were sent, either attack or not attack. But the probability of one versus the other does not change as far as you're concerned, even if you see the ciphertext. So it's perfectly indistinguishable. M and M prime are perfectly indistinguishable. People okay with this definition? Okay, so the first one is that really you've got no information on the message that's being sent. The second one is you can't distinguish between two messages having seen the ciphertext. So which is the right definition? Both are very strong. You know, this one talks about for every pair of messages and for every ciphertext. Which one do you prefer? How many people prefer perfect secrecy? Chat the first one. Okay. How many people prefer the second one? Yeah, I was told that if you have a really lousy vacation, all that matters is the last day. So this is the second definition, so you like that. I mean, the last day is good, then it was a good vacation. But in any case, the truth is that these two definitions are equivalent. Okay? So we can show that if an encryption scheme satisfies perfect indistinguishability, the second, it also satisfies the Shannon one, the perfect secrecy, and vice versa. So we can show that any scheme that satisfies the top one will satisfy the bottom one, and vice versa. Formally. So these definitions are equivalent to each other. And I was going to go through the proof, but I would like to just delay that. If we have time, we'll go through it. But it's in the slides and in multiple notes. It really uses a simple conditional probability and Bayes theorem. Simple rules of manipulation. But let's understand the meaning of it. It means, first of all, that it gives us more confidence that either one of these definitions, that they were the right definition. Okay? Because they both kind of make sense intuitively and they're equivalent to each other. The second thing is that often you will see that one definition is easier to work with than the other. And it so happens to be the case both for Shannon's, okay, in the proofs and definition, and even later in the course we're going to have these type of indistinguishability definitions often come up. We talk about pseudo-random numbers that are indistinguishable from random numbers, like the two ciphertexts of two different messages are indistinguishable from each other. This indistinguishability kind of thing comes up all the time, okay? And it's a very easy, technically, thing to work with. If you know that a scheme satisfies indistinguishability, often it's really easy to work with that definition in order to prove some things. And then it would follow that it's also true for perfect secrecy, right? Because the definitions are equivalent. So sometimes, you know, we have 10 definitions, they're all equivalent to each other, but you'll see that people only stick with one because it's a much easier, nicer definition mathematically to work with. And that's going to be true about the indistinguishability. Okay, so in your homework, your first homework, I think problem 1 has a lot of this type of games, right? We take a definition, we change it a little bit, and we ask, is it still equivalent? Can you achieve it? Can you not achieve it? So as a first exercise, before you do that, I would actually go through the proof, which is on the slides or in the notes that we're in now. How do you prove the two definitions are equivalent? In this class, I mean this lecture, really, it's all using elementary probability theory. You know, Bayes theory. Remember Bayes theory? So probabilities of some event A given some other event B. Just have it on the next slide. This is really kind of the only thing you need to know. And to think, you know, the probability of some event A given event B is the probability of B given A times. So that is almost in some sense the only kind of math fact about probabilities that you're going to need in order to prove that. And also the fact that you sum up all the probability of a message in the message space, you sum it up over all the messages, you get one, right? So sum of any happens. And basic probability rules. So here's the proofs. I don't want to do that unless we have time. Okay? So we have a definition. That's nice. Can we achieve it? So some of you have already referred to the fact that we can achieve it. I actually referred to the fact that we can achieve it. So it's a very strong definition. It means that the ciphertext tells you nothing, really, even if you're unbounded adversary. And the beauty of it is that you can achieve it. How do you achieve it? So the scheme is, I have to describe to you what the scheme is. That's what we call the ABC of crypto. And that is a scheme called one-time pad. What's a one-time pad? It could be that many of you know it. So I need to specify what G is, what A is, what D is, right? It's an encryption scheme. So one-time pad, so first of all I have a security parameter here, which I guess I use L for it, okay? L is what K used to be. And this line is L for length, okay? That's the security parameter. So L is the security parameter. Our alphabet here is going to be 0, 1. So we're really always going to talk about sort of binary strings, okay? The key is a binary string, the message is a binary string, the ciphertext is a binary string. You can't get more general than that, right? You express everything this way. So what the G does is that it chooses, so it takes one to the L, which is the security parameter, and what it does is it chooses the secret key, chooses the SK at random in 0, 1, 2. So it just flips L coins, right? Writes down the results, that's the secret key. So every key comes up with what probability? 1 into the L, right? So it's 100, 1 into 100. So that's the probability of every single key. And what does the encryption algorithm do? Remember, it takes a message, it takes a secret key, and it takes a message. And for the one-time pad, we're going to think of the key, the message, and the ciphertext. They're all L-bit strings, okay? They're all binary L-bit strings. So M, A, C, and SK are all going to be L-bit strings, okay? Remember of 0, 1 to the L. So what this guy's going to take is an L-bit secret key, an L-bit message, and all he's going to do is he's going to take and he's going to XOR those two. So it's two strings, so it's bitwise XOR. So right, so if the secret key was 1, 1, 1, and the message is 0, 1, 1, then the result of applying the encryption, so the ciphertext is equal to that, is going to be adding mod 2, so 0, 0, 1. You with me? So I just bitwise XOR the secret key and the message. Now, is this deterministic or probabilistic? This encryption algorithm. Deterministic. I don't toss any coins or anything. I just take the secret key and store it with the message. So there's one output per the input. And what about decryption? We take the secret key and the ciphertext. So very nice, because how do I get back from the ciphertext and the secret key the message? I just XOR the ciphertext with the secret key, right? And that has the effect of canceling out. So it's like secret key toward M, so the secret key is just getting back the message. So it's certainly correct. Are you with me? Okay, great. What about security? So I claim that this one-time pad is the best encryption scheme ever because it achieves perfect secrecy. And the proof is so simple, too. What is the proof? So in order to achieve perfect secrecy, what do we have to do? If we look at that definition, it says that for every little m, for every little c, this is the a priori and the posteriori are the same, right? So let's fix a particular m and c, okay? And let's see what is the probability, because over the secret keys, that the ciphertext ends up to be little c. Okay? So this is once we fix the message we're sending, what is the probability that it really is the ciphertext you would end up with? Well, it's just a probability that if you took this, whatever choice of secret key you took, and XOR with the message, you would come up with little c, right? So M is fixed, the message, the ciphertext is fixed. So what's the probability? That's really the ciphertext that we would end up with. It depends on the key. Okay? So essentially, there's only one secret key that will make this true. Right? It's the secret key, which is equal to M XORed with the ciphertext, which comes up with probability 1 into the M. True? So once you fix the little m, you fix the little c, there's only one secret key to make this the case. That happens probably 1 to the L. And this is true for every message, right? So for m, it's true for m prime. So for every c, m, and n prime, this is the case. The probability is 1 into the L. You with me? So this 1 into the L is true regardless whether m was little m, the message I chose was little m, or the message I chose was little m prime. Okay, there's a different secret key that will make it true, but it's still with probability 1 into the L. So we have achieved actually distinguishability. So from seeing the ciphertext go by, and I would like to know in my head, is it m or m prime? Well, there was a key that could have made it b little c from m, and there was a key that could have made it b little c from m prime. And these keys come up with the same probability. So as far as I know, seeing the ciphertext, I have really no idea. You see that this is, even if m is zebra and m prime is hello, so even though these zebra and hello have very different probabilities, from the ciphertext, I can't tell which is which, because there was a key that could have made zebra send this C, and there was a key that could have made hello send this ciphertext. All right, and once we've done indistinguishability, also Shannon secrecy follows. So here's an example where indistinguishability was much easier to prove. It's sort of trivial. You know, the probabilities are the same. Done. Are you with me? The one-time pad is wonderful. We love one-time pads, okay? Okay. Now the message, this question you ask, what if I want to send another message? You know, I mean, I'm not, you know, we're doing all this work, we meet in advance, we agree on a key, we toss all these coins, now I send you zebra, you know, now I want to send you giraffe, you know, and you know, can we do it? Well, we could try. So we could do the same thing with one-time paths. So we had one message, this was the key, let's say, and this was message M, and now this was zebra, and I want to send you giraffe. So I take the secret key, and let's say giraffe has the code, I don't know, 100. So I do the same thing, 110, and I send this. So this is the first ciphertext, and this is in prime, and this is the second ciphertext. I could do it. The only question is whether it's still secure. Okay? What does it mean secure here? Well, first of all, it isn't. It's not true anymore. The perfect secrecy is satisfied. Okay, so we're, here's an easy way to see it, and that is, let's think about a message as being built up of, let's think about the message as being built up of two blocks, okay? So this is an L-bit message. Let's say the first half of this is L over 2 is M1, and the second half is M2, okay? M2. And the second M prime is M1 prime and M2 prime. And we're gonna show particular choices for M and M prime, okay? And a particular ciphertext. So in order to violate perfect secrecy or to violate perfect distinguishability, how do I violate it? All I have to show you is that there exists some M, M prime, and C for which this is not true anymore. Same thing for your homework. To show that something is not satisfying a security definition, all you have to show that it's violated for a particular maybe setting of messages, of keys, of ciphertext. Okay? So I just have to show you a choice for M, M prime, and C for which this is not true anymore. That once I see the ciphertext, I wrote it this way, but it's really indistinguishability is violated. That given M, the probability of a particular ciphertext is different than given M prime. Okay? So the idea is that the following. Let's set our messages to be the kind where the first part, M1 and M1 prime, are the same. Let's set M to be a message where the first block and the second block are the same. Just repeat, like giraffe, giraffe, okay? Whereas M prime, that's not the case. So M1 prime and M2 prime are different. So in other words, I'm taking, my choice of messages is M is something where the first half and the second half are exactly the same, okay? And M prime, so let's think of this as XX, is X or Y prime, okay? That's the only condition that I need about these messages in order to violate this perfect indistinguishability. Because what's going to be the case? Obviously, if what I did is I took my one-time pad, which was, so this, I'm thinking of this as length L, and this is length L. Okay? So this is length L, and this is length L. Because we're talking about using the one-time pad twice to XOR the first, each time I XOR the same one-time pad. So obviously here, if I XOR this guy with the one-time pad, okay, and I XOR this part with the same one-time pad, I'm going to repeat the same, the ciphertext is going to look like the first half and the second half are the same, right? In other words, the ciphertext for the first message and the ciphertext for the second message are exactly the same. If I send the same message. Whereas here, they're not going to be the same. Because Y and Y prime are different. Okay? So in particular, there is some ciphertext, okay, which is the repeats itself, okay, which will show up in this case, but won't show up in this case. Okay, so there exists a ciphertext, which violates here the definition, such that it will not come up with the same probability for these two messages. The messages where the first half and the second half are the same versus the messages the first half and the second half are not the same. Are you with me? Again, all I have to show is that there is some pairs of messages. In this case, I'm thinking about the message as like two messages. So I'm comparing two messages versus some other two messages. And as long if these guys are repeats of each other, the first and the second, here they're not, then there is a ciphertext which is not the repeat, which will not show up with one, but will show up with the other, and therefore the probabilities of that ciphertext coming up are different. And we're violating indistinguishability. So it's a bad idea to send the same, to use like the one-time pad twice without changing it. So what does that mean? That seems to be, give us a problem. What if we wanted to send two messages, like zebra and giraffe? What if we did? We would have to meet again, I guess. Or maybe we don't use one-time pass. Maybe there's another encryption scheme that can do it, that you can send multiple messages, okay, and you don't have these kind of problems. So are people with me? I proposed a scheme. It was wonderful for sending a single message, but as soon as I want to extend it to sending two messages, there are problems. Now, this problem may seem artificial in the sense that this goes through the definitions, and you can distinguish the fact whether this thing repeats and this thing doesn't repeat, and who cares anyway, okay? Well, you may care to hide the fact that the same message was sent twice, or that the last few bits of the same message, the first message and the second message are the same, or that each other complement. There's a lot of relationships that you can find out here between messages, okay? So maybe there's another scheme, one-time pad prime. So what Shannon showed is that that's not the case, okay, in some sense. What he shows is that no matter which perfect secrecy scheme you're going to use, okay, whether it's one-time pad, or one-time pad prime, or one-time pad double prime, in a sense, you're going to have to meet again and again and again if you wanted to send messages which are longer than the size of the key. Because remember, in the one-time pad, I knew that I was going to send you L bits, so we sat together, we flipped L coins, and we set the key. Now I want to send you 2 L bits. With one-time pad, we could meet again. Or we could have, to begin with, agreed on a key which was long enough to support all messages we ever want to send. So we would have to know in advance how many bits we ever want to send, right? How many messages, and we flip enough coins for the key. What he shows is that is inherent. So in other words, the number of keys really that are possible, this is the title, but if you think about it, the size of the key space, okay, the size even of the bits that describe the key is the same as the size of the message bits that you're ever going to send. So if you ever want to send 1,000 secure bits, you in a sense have to decide on a 1,000-bit long key. So how do you prove that formally? Maybe there is something, a scheme that we didn't find out about, that with all our brain power at MIT and so forth, there is another scheme. You have to prove that this has inherent limitations. Okay? And this is the proof here. Again, we ran out of time. It's a simple proof, but it's probably more complicated than anything else that we talked about today, so I'll just give it 1 minute, okay? we kind of say the following. We prove it by contradiction. We say, suppose that's not true. Okay, there is actually a scheme where the size of the keys of the size of the key space is less than the size of the number space. Okay, and we derive a contradiction, and then you know, essentially you just go through it because it's technically bad. But I think it's followable. We show essentially that again a violation of perfect indistinguishability. That if you did that, okay, it must be the case that there is some ciphertext, okay, which is more likely to come up in the case of some message M than in the case of some other message M. So exhibit a C and M at a time that violate perfect indistinguishability. And that's the lesson. So what does that mean? It means that the spy has to carry a suitcase with lots and lots and lots and lots of bits to specify the secret. If you want perfect